All right, welcome. I'm Ryan Holger with Temperature Equipment Corporation. Today is October 28th, 2013, and this is our regular Monday webinar. This week's topic is radiant heating and snowmelting systems, so we're going to give you guys a primer on that. Before we start that, I did want to kind of show you the remaining schedule for webinars for this year. As you can see, we've done a boatload of them throughout the year, and we are currently in the final stages here. We have 4 to 6 more webinars to go, depending on how some of the TBDs turn out. Next week's topic is RGF air purification, and we got infrared versus unit heaters, modulating gas furnaces, and hourly analysis program HAP for load calcs and energy analysis purposes. We are getting ready to start planning out the 2014 webinar schedule. So if you have ideas on things you'd like to learn, please go ahead and email them to me. I will throw my email back up on the screen here right now. Or if you wait a little bit, somewhere between Thanksgiving and like the second week of December, you should receive a survey email asking you what you like and don't like about our webinars and training classes and what stuff you'd like to see in the future. All right, so with that, I'm going to go ahead and jump into it here. Like we said, this week's topic is radiant heating and snowmelting. And we'll touch a little bit on radiant cooling, but just for background purposes, we're not really going to cover that in too much detail here. It's a whole other topic in itself. So one thing I want to mention, in case people don't know, because a lot of you still ask about it, is a little over a year ago, the Department of Energy rules for manufacturing boilers changed, and the new minimum efficiency for smaller boilers, which means under 300,000 BTUs, those boilers do require an 82% AFUE minimum for hot water boiler systems. So that's one rule change, and that one's pretty easy because the manufacturers have to do that. The other rule change is that there's no standing pilots allowed. That one's also pretty easy because the manufacturers have taken care of that. We've got spark ignition type devices now. Then the third rule along with that change, which does require some thought and process from the design engineers and installing contractors, you have to have a means for automatic water temperature adjustment. Generally speaking, that means outside air reset control. So we will talk a little bit about outside air reset control today, both for regular systems and radiant systems, which is today's agenda. There are some manufacturers who are doing it with non-outside air control mechanisms, like Utica down in the bottom right-hand corner. That boiler there has some staging algorithms that are trying to change the water temperature set point, a little bit different way to try to attack it. But for most of the boiler manufacturers, outside air reset is the way you'll be doing it. So this chart here, I believe we took this one out of the ASHRAE handbook, so we apologize for stealing it and we give them credit. But this gives you kind of an idea of the boiler return water temperature effect on boiler efficiency. This is for a sample boiler, not a specific brand of one. The bottom of the chart there goes from 40 to 240 degrees, and that's the inlet water temperature to the boiler, so the return water temperature. Up the left side goes from 80 to 100% efficiency, and that is the boiler efficiency itself in terms of how much goes into the water, how much goes up the stack. So if we look at a regular hydronic system, which is typically designed for 180 degree supply water and a 20 degree delta T, which means 160 on the return side, right? So where do we end up on this chart? 160. This is an 86% efficient boiler, which is a very nice boiler. If I ask it for hotter water, it gets a little bit less efficient. If I ask it for cooler water, it gets a little more efficient. Then I get to this magical point here where my little red dot's at. Hopefully you guys can see the red dot. I get to that magical point at approximately 130 degree entering water temperature, and my efficiency spikes up dramatically as I get colder, right? Because then my boiler is entering a condensing mode. The return water temperature of the boiler is cool enough to cause the flue gases to condense in the secondary heat exchanger, or in the case of a non-condensing boiler, in the regular heat exchanger, to condense in the heat exchanger and save that latent energy in the boiler instead of letting it go up the stack. So we get a huge spike in efficiency. So the reason I'm showing this to you is most of you guys have probably seen this chart before or a similar one, is the more hours we can operate with cold return water, the more efficient our boiler plant becomes. If I design all your plants for 180 supply, 20 degree delta T, I'm going to pretty much get the rated efficiency of the boiler. But if I can get that boiler to operate at colder temperatures, either for all of the year, such as outside air, all the year, such as radiant, or part of the year, outside air reset, I'm going to be much more efficient. So a radiant system, if you think about it, I can't send 180 degrees to the floor. right? Because 180-degree floor is going to be really hot for people to stand on and extremely uncomfortable. So usually I'm kind of limited to like 110, 115, maybe 120 supply, which means I got, low hundreds for my return water. So even on my normal radiant system, I'm already making this 86% boiler look like a 92, 93% efficient boiler. And then as I reset the water temperature lower, it gets even more efficient. So a radiant system is going to make your boiler operate more efficiently than it's rated, just for the simple fact that I'm going to have a cooler entering water, which is causing the condensation to happen earlier. Now, if you got a non-condensing boiler, you can't allow that condensation to happen. You're going to have to put a mixing valve on there in order to get the cool 100-degree water for your radiant system, but that doesn't really help your boiler efficiency. So as soon as you say you got a radiant floor system or you have a snow melt system, a condensing boiler becomes an absolute no-brainer, and you would use that in all situations unless you happen to have another boiler there and you're just stealing like waste heat off of it for some reason. But anytime you're designing anything new, if it's radiant, you definitely want a condensing boiler. Putting a non-condensing boiler in is going to cost you more in mixing valves than it would have been to just buy the condensing boiler up front. All right, so hopefully that makes sense. This shows you an example of a normal outside air reset curve for a non-radiant system. So think of this as traditional radiators or baseboard or air handler coils or something like that. So the way it basically works is on the bottom here I got my boiler supply water temperature from 120 to 180 on this chart, and up the left I got 0 to 60 degrees outdoor temperature. So if it's 0 degree design day, I follow along my chart, boom, 180 degree supply water. So if it's 0 or colder outside, give me the full design 180. I need full heating. If I look at the other extreme, 60 degrees outside, give me 120 degree water. I can pick anywhere in between. If I pick 30 degrees outside, follow my chart along, boom, 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 150 degree water, right? If it's 10 degrees, I get whatever, I don't know, 168 degree water or whatever it comes out to be, right? So as the outside air temperature changes, my supply water changes. The more hours I can operate with the cooler supply water, the more hours I can get in this high efficiency range, right? So that's kind of the goal of normal outside air reset schedule. But knowing that there's some hours that I got to have the full 180 type temperatures in order to heat my space. Well, with a radiant system, I could still do the outside air reset. The difference is I'm never going to have 180 degree supply water because that's going to be way too hot for people to stand on. So I'm kind of be going from that like 90 to 115, or in this chart we got 85 to 110, right? 0 outside, give me 110, 60, give me 85, and I can obviously do anything in between there. Well, if 110 is my supply, it means my return water is like 90, 95 on the coldest day of the year. So 90, 95 return water, I'm right here. My 86% boiler in this example starts looking like a 95, 96% efficient boiler. So some of the boiler manufacturers, when you look at their literature, they'll tell you what the thermal efficiency percent or the AFUE percent rating is, and then below it they might put in parentheses, hey, this is a 94% efficient boiler, parentheses, 98% on a radiant system or something like that, because they know they're going to be operating at a cooler return water temperature, and hence making it more efficient. So that's one of the many reasons why a radiant system is more efficient to operate than a traditional hydronic system would be. We'll talk about a few other ones as we kind of walk through here. All right, so saving money is obviously one goal of having a radiant system, but the main driver in most cases is a comfort effect. There's lots of things that affect people's comfort. Right now we're going to mention some of the things that make you uncomfortable. One of them is temperature swings in the space. Right, I'm dumping 120 degree air out of your diffusers. It's warming up your space. Then I'm shutting off that air. It's cooling down, turning it on, off, on, off. That cycling effect, people perceive that, and it's an uncomfortable, unpleasant thing to them. Going from one room to the next when the temperature is different, they can perceive that. Usually anything that's about 2 to 3 degrees or more difference in temperature, people can feel that with their skin temperature. Right, so people notice that kind of thing. People, in terms of airflow, in the summertime, you kind of like the diffuser airflow blowing on you. It kind of helps cool you off a little bit, takes the heat away from your body. In the wintertime, it's the opposite. You pretty much want no air blowing across your body. You'd prefer not to have an air-based heating delivery system if possible, because it's going to give you a cooling effect with the evaporative effect of your skin, not to mention the convective effect. So you don't want that to happen. You'd rather have a system that does not move air at all for the heating season, if possible. Now, obviously, you still got ventilation concerns and things like that, so you're going to have some airflow, but minimal is best in terms of heating. Touching cold surfaces. If it's summertime, you like walking on the cold tile floor of your kitchen or whatever. But if it's wintertime, cold surfaces feel cold. Conductive heat transfers directly up through your feet into your body. Whether this happens not just at the home example like we're showing you there with the people in the slippers, but it happens at work too. If you're standing on a slab floor like I am right now, and the slab in this office is about 58 degrees, and I know that because I measure it because I'm anal, right? 58 degrees does not feel cold going up through my feet all day long. Not feel good, excuse me. So there's things like that that kind of affect your ability to be comfortable. And some of these are just pot shots at air systems, so we won't read all those out loud. Sound is actually a good one, right? So if it's an air-based system, you're going to probably hear some sound coming out of the diffusers, if not, the air handlers themselves. If it's a hydronic-based system and it's radiators and baseboard, you are more likely to hear sound traveling through those pipes than you are to hear pipes traveling through the concrete floor, right? The concrete acts as a sound insulator, and it's not probable that you're going to hear anything on a radiant floor unless the boiler room is on the other side of the wall from your head and you have a loud boiler, right? So a radiant floor is going to be more quiet than any other heating system that you could probably come up with. And you have more flexibility with how you move things, desks and furniture around the office space or at home, couches and things like that, because the whole floor is a giant radiator to you, right? So that's kind of one of the goals of these radiant systems. So we can get rid of some of the sound noise issues. We can keep the temperature significantly more even than we can with any air-based type system, and it actually is warmer when you're actually walking on it. So a lot of you guys probably know about ASHRAE Standard 55, which is the thermal comfort standard that we kind of follow as a country. Actually, some of you guys may not know anything about it, but you guys that are on the engineering side probably babysit that standard like you do other ones, or if you've done a lead project, you probably had to adhere to that standard to get the additional points. There's lots of things that go into ASHRAE Standard 55 standard for thermal comfort for human occupants. Everybody probably knows air temperature is a big comfort driver, right? And you probably know humidity is a comfort driver. I'm sure you've talked about both of those things with your clients before, right? But there's several other factors involved, not just dry bulb temperature and humidity, but also the mean radiant temperature is a factor in that formula for ASHRAE Standard 55. Air movement is a factor, clothing level, activity level. There's several things that determine whether you're going to be thermally comfort or not. And one of the things that standard also dictates is that from the floor, or they give you a little buffer, so from a few inches above the floor to the top of your head, you can perceive you want the occupants to perceive no more than a 5-degree difference in temperature. If it's more than 5 degrees, people will perceive that as their feet being cold or their heads being hot, or both, right? And that's going to be an objectionable thing. And as you guys know, for that standard, you got to get 80% of the people to be happy in order to really comply with the standard. We realize 20% of the people are crazy and you can't help them, right? So a few inches above the floor to the top of your head. If it's seating occupants, we say from 6 inches to 3.5 feet. If it's a standing occupancy area, 6 inches to 6 feet. No more than a 5-degree difference in temperature from head to toe, or people will feel that and they will complain about their comfort. Well, if I have a forced air system, whether I'm heating from the ceiling or the floor, and especially when I'm heating from the ceiling, I'm going to have a very difficult time achieving that. If I'm dumping 100-degree air out of your diffusers from the ceiling, and I'm trying to satisfy a thermostat on the wall and make it 70, well, if it's 100 at the ceiling and it's 70 at the thermostat, logic dictates down at the floor it's going to be something cooler than 70, right? And probably significantly cooler, probably high 50s, low 60s. It's very common for an overhead forced air system. Floor delivery systems are a lot better than overhead for heating anyway. So residentially, we do a little better with this. Commercially, we typically heat from overhead because it's a cooling-driven application, and heating is kind of a side thought usually. But the point is, with an air-based system, I'm not going to be able to keep that 5-degree delta T between your head and your toes. So it's going to, in general, be less comfortable. Radiant systems are really good about it, right? Because radiant heat, as you probably know, is delivered quite a bit differently than air-based heat. Air-based systems are primarily convective heat, right? So that's air motion, using air as the heat delivery mechanism. There's also conductive heat, right, which is touching a surface, excuse me, like putting your hand directly on top of an electric stove, right? That would be conductive and stupid, by the way, right? So conductive, convective, and radiant are 3 main ways to transfer heat, and then the fourth would be evaporative, but that doesn't really apply in this scenario for heating. Radiant heat delivers heat via line of sight via infrared, right? So if you go outside on a 60-degree day when it's sunny, the radiant heat of the sun makes your body feel warm. It's 60 degrees outside, which isn't great, but your body feels warm. If it's 60 and cloudy, same exact air temperature, your body feels cool, right? So 60 degrees, cloudy or sunny, it's the same air temperature. My thermometer registers it the same. My body feels different because of the sun. Same exact thing if you were sitting at a campfire, right? It's 40 degrees all around you on every side of your body at the campfire, but the front of you is absolutely roasting because you're staring at the fire, right? Literally burning up. Your backside is freezing, right? Same air temperature on both sides, but the radiant effect warms you with that infrared. So the same thing happens in your house. If you were to put a radiant floor in your house or in your commercial building, that floor is going to be shining on you with infrared radiant heat, warming you up. Additionally, the radiant floor is emitting that heat and shining on all the surfaces. So it's shining on the wall and the desk and the chair and everything else in there, warming those things up, making them re-radiate back to your body. So we do a significantly better job of being able to heat you with radiant heat than we do by heating up the air. And it's such a better job that you're actually able to lower the temperature set point on your thermostat. I don't know if any of you guys live in radiant floor houses. If you do me a favor, in the bottom of the screen there, type in the temperature set point you keep on your thermostat for your radiant. On the air side, a lot of people keep it in that like 72, 73 degree range. Some of you guys like it cooler and you might keep it like 69, 70. I'll see if anybody types in on the screen here. But most of the people I talk to that have radiant heating in their houses, including some of my coworkers here, most of them keep it between 62 and 67 degrees on their radiant stat. So on average, you could say it's like 3 or 4 degrees cooler that you keep your radiant system than your air-based system, because you got the radiant effect warming up your body and not just the air warming up your body. None of you guys must have a radiant system because nobody typed anything in. Oh, there you go. Matt types in 62. I use 62 degrees regardless of the wife's complaints. Matt, you might want to try 64, buddy. Might help you out a little bit better tonight. But 62 degrees, right? And if he had an air-based system at his house, I'm sure he would not keep it at 62, because then the wife would complain so much she would leave, which may or may not be Matt's goal. I don't know. Thanks for typing that in, Matt. All right, so that's kind of the difference with radiant heat versus convective air-based heat. Right, so your feet are warm, your lower body generally stays warmer. And for women, by the way, Matt, this helps out quite a bit, because for men, our main temperature sensing points are typically our wrists and behind our ears, which, oh, conveniently, are kind of in line with the thermostat at the office, right? Women, their main sensing points, regardless of what your buddies probably tell you, their main sensing points are their ankles, right? And the ankles are very close to the floor where it's cold. Plus, for some reason, in all these office buildings, women like to wear open-toed shoes all year long, which makes no sense, but that's what they want to do, right? So they're always complaining that it's cold, and they all got the electric space heaters under there, and the guys are always complaining it's hot, right? By the way, I've never seen an electric space heater on an office floor that had radiant heat, right? If they got radiant floor heat, nobody's using electric space heaters. So you're saving money, keeping a lower temperature set point, and actually keeping people warmer. It's kind of weird, but that's kind of how it works. This kind of gives you an example of just looking at the temperature, air temperature, and radiant temperature portions of like the ASHRAE standard 55, and kind of ignoring humidity and all those comfort things for the moment. So if you look at it here, on the left scale, the vertical scale is room air temperature from 40 to 90, and mean radiant temperature, mean meaning average radiant temperature from 40 to 90, of my surfaces in that space. Those pink bars are when you graph out the ASHRAE standard to graph out when people are actually comfortable, right? So, and we kind of drew a magical line here saying convectives on one side, radiants on the other. You can move that line a little bit either way, but you kind of get to see the idea that the pink bar is really, really thin over here to maintain comfort. And in fact, if I'm trying to maintain comfort, in this range typically, right, where I got my little John Madden highlighter over here, if I want to use, hotter air temperatures, then I could have cooler radiant surface temperatures, right? But if I want to have cooler air temperatures, like in this case 70 degrees and below, then I need warmer radiant temperatures, right? So I can kind of trade these things off. I can either have hotter air and cooler surfaces, or I can have cooler air and warmer surfaces, right? And the band, by the way, is quite a bit wider. Let's see if I can. I didn't want to do that. The band, by the way, is quite a bit wider over here on the right-hand side, so it's an easier target to hit to make someone comfortable. These are pretty thin goals to begin with, but it's easier to hit it with the radiant side than what it is with the air side, and it costs you less energy to do that. Right, so the mean radiant temperature, or MRT as we're calling it here, it reduces the heat loss from your body. Your body is a radiant heater. It is transferring heat from your body to other objects, exactly like the sun radiates heat to the earth, exactly like the campfire radiates heat to your face. Your body is radiating heat to all the colder surfaces. So if you're walking in your house or your office and you walk by your crappy single pane glass window, it feels like, wow, that window's like throwing a lot of cold air at me. Not really. That window's sucking the heat away from your body, because your body automatically, or any heat surface, automatically transfers from hot to cold thing. So your body's the hot thing, 92 degrees skin surface temperature, going to the 60-degree glass temperature. It sucks the heat away from you very quickly. So if all the radiant surfaces, meaning my floor and my couch and my work desk and any of those things, are warmer, my body gives up the heat slower, which is exactly what I want in the wintertime, right? So it is a significantly more comfortable way to keep things evenly temperatured throughout the building. All right, so hopefully that makes sense to everybody here. Generally speaking, cooler air has a higher relative humidity. It's not higher grains of moisture necessarily. It's typically a higher percent relative humidity, right? Because cool air holds less humidity, warm air holds more humidity. So cooler air with a certain quantity of moisture in the air might be, 50% RH, but that same quantity of moisture of air in warmer air may be 20% RH, right? And relative humidity, the RH, that's the part you feel, right? So if I have cooler air, if I keep your stat set at, in Matt's example, 62 instead of my house, which is a furnace, and I keep it at 69, right? If I keep it at 62 instead of 69, the relative humidity percent is actually higher, and I feel that difference, right? So there's not as much static electricity, there's not as much, dry throats and dry noses and that kind of stuff. And so I'm not even adding a humidifier. It's very rare for us to do a residential radiant system and add a humidifier to someone's house. Generally, we don't need it. We may need an ERV to bring some ventilation air in, which is a whole other discussion, but I generally don't need to add a humidifier. Right, so that's kind of the goal there. On the positive side, I don't need any ductwork to do the radiant heating. I'm probably still going to need it for my cooling season and my ventilation, but I don't need it for the radiant heating. We're kind of showing that here as a benefit because we're not moving air around quite as much, but there's also a negative story to that side, which means I'm not filtering it as much if I had a good filtration system, right? So I may be having my ERV and a small filter just to kind of bring fresh air in and do that kind of work when I have my radiant system. All right, so kind of going to keep on moving there. So in terms of laying some of these systems out, we'll talk about a few guidelines and rules of thumb kind of thing. Every heating and cooling system begins with the load calculation to determine what I want, and we'll talk a little bit about that kind of stuff, that process in a few minutes here. But just to kind of get you some check figures in your head. So on average, a typical residential application, we're typically doing about 250, sometimes 300 feet per circuit. It's a little bit different with commercial, because with commercial we tend to use slightly larger diameter pipe, and we tend to space the tubing a little further apart. So maybe instead of 9 inches on center, maybe we're doing 12 inches on center, and using larger tubing. That means the floor is not going to be quite as evenly tempered as it be in a residential system. Right? I may have a little bit warmer spot, and then a few inches over I may have a little cooler, and then a few inches over warmer again. Residentially, we like to keep the tube space pretty close because people like to walk around barefoot. Oddly enough, one of the selling features for having a radiant heated floor in your house is you can walk around barefoot in the winter. So that's kind of what people want, so we kind of do it that way. So it tends to dictate, we put the tube in closer, which means smaller diameter pipes, which means not quite as much distance on the circuit. The larger commercial ones, we spread it out a little bit more because you got typically a layer of carpeting, and then you got shoes on and stuff like that. But for sake of argument, 250 to 300 feet per circuit. If you try to do longer circuits, you are going to regret it because you are going to have a giant ass pump to handle all the pressure drop of the pipe, right? And then B, you're probably going to have to run a little bit warmer water at the beginning so you don't use it all up by the time you get to the last, section of radiant floor there. So tend to limit to smaller circuits. It doesn't mean I have to have one zone for every 250 feet or whatever. I can have one zone that has 3, 4, 5, 10 different circuits of piping on it, right? Zone meaning the thermostat, if you will. So one zone can handle this whole, section of the building, one stat, but I might have, say 5 circuits on that section, 5 loops, if you will, going back to a manifold like we're showing over here. All right, so on this one we got 1, 2, 3, 4, 5 individual piping circuits, and let's say they're all 255 feet, right? We got a supply header, we got a return header coming back, right, and those headers are going over to my boiler plant. But this could all be controlled off of one zone, right to the left of this header where my little red dot is. I could have my zone valve or my zone pump, right, and that guy's basically turning on and off with the thermostat to allow water to flow through all 5 of these circuits at the same time. All right, or I could individually zone each of these 5 circuits if I wanted to do that, because of my application. So that's kind of the deal with that. We generally do not use programmable thermostats with radiant floors. And by generally, I mean don't ever do it. You are going to regret it. A lot of you guys have probably heard me preaching about needing programmable thermostats for code compliance. If you actually read the International Energy Conservation Code, you will see that there is an exception for these kind of radiant systems, that you do not have to have the programmable stat. There's a couple reasons for that. From an energy standpoint, right, you're already getting a boatload of energy savings because you have a lower thermostat setting, right? Matt keeps his at 62. I keep mine at 69. He's going to spend less energy to heat his house. If his house is 62 degrees, the heat loss from inside his house to outside his house is less than me on a 0-degree day, right? Because heat goes from the hot thing to the cold thing, and it moves faster as the delta T is larger. So 62 to the, let's say, 10 degrees outside, or 69 to the 10 degrees outside, my house will lose the heat faster than Matt's house, right? That's how that's going to work. So I already got the energy saving benefits of just having a radiant system, so not needing the programmable stat to get me the benefits of energy savings. But the other thing is that when you start heating one of these floors up, especially a concrete radiant floor, which is what most of them are, right, it may take 8-10 hours to get this floor heated up, right? And it takes 8-10 hours to cool this floor down. Right, so someone trying to set their programmable thermostat is never going to get it right, and they're going to abandon it almost immediately anyway. Right, you're going to have to say, okay, I want my system to turn on at midnight, so when the kids get up at 8 a.m., we're good to go, or whatever time the kids get up. And the same thing, okay, we're going to shut it down at 5 p.m., so when I go to bed at midnight, everything's fine. Right, so you really cannot use a programmable thermostat with a high-mass system, high-mass radiator system, and in this case, a high-mass a concrete floor or even a wood floor with radiant tubes is going to be high-mass. The response time is too slow. That's also the benefit, right? That's why we have such even temperatures, because it takes a long time to heat it up or cool it down. We do a lot of applications in places that have opening dock doors, right? So we do it in warehouse spaces or manufacturing plants where the dock doors open. We do a lot of car washes, right, where I have basically outside air getting sucked in all the time. Every time that thing opens up, the door opens up for a car to come in. If I heated those kind of places with air, you open up the dock door, all the air sucks out, and there goes all your heat. With the radiant floor, you're heating up the concrete, this big giant mass, and that mass, by the way, is radiating to all your shelves and products and everything like that, and they become re-radiators. So when I open up the dock door, I don't lose that heat hardly at all. So it works really well. That slow response helps us sometimes, but it does not help us if we were thinking about using a programmable stat. We can basically put radiant tubing anywhere we want. So we talk about it a lot, putting it in the floor, because that is probably one of the more comfortable ways to do it. When we talk about radiant cooling systems, large commercial buildings, we tend to put it in the ceiling, right? Because cooling from overhead and heating from the floor tends to work out better in general, But it can be anywhere. I could put it in the floor. I could put it in the ceiling. I could put radiant tubing in my walls. I can put it into gadgets like my towel bar in my bathroom or something like that. Right? I can kind of stick this tubing anywhere that I can stick this tubing, and it's going to heat a room pretty well evenly. But in the floor tends to be the most common spot. Generally speaking, radiant floor systems don't do great with carpeting, and certainly not thick carpeting. The carpeting acts as an insulator. So in a normal building, right, or a normal house, thick carpeting is great. It keeps me a little bit warmer because I don't lose as much heat to my basement floor or to my slab floor, right? But with radiant, it's kind of the opposite. I want either no carpeting, right? So I want, you know, thin layer of wood, or I want painted concrete, or I want tile is a great one, because those will transfer the heat up to me very nicely. We can use the radiant as our primary heating and only system. There's nothing wrong with that. You can certainly do that. A lot of houses don't. A lot of houses use it as a primary and then still have a secondary heating system. That secondary heating system is typically a fan coil with a hydronic heating coil being served by the same boiler. And the reason for that is on a mild day when it's, 55 degrees outside, in the morning you may want to temper the air a little bit because it's kind of cool, but you don't want to turn on the full slab and wait 8 hours. So kind of in those collar seasons, it's nice to be able to run your air handler and do a little tempering. Plus, you probably need the air handler anyway for your ducted cooling system and for your ventilation needs. So you probably need that anyway. So sticking in a hydronic coil after you've already bought the air handler and ductwork and all that, it's a pretty minor expense in the grand scheme of things. But we may use that little air handler for the mild days, and then when full-on wintertime comes, like we're getting close to right now, we turn on the radiant slab floor and let that be the primary heat the rest of the time throughout the year. You can also use it for floor tempering. So if you just want to if you want to add in some radiant heating in a space, you can do that and temper the floor. This is more common in residential where people want their kitchen floor and their bathroom, powder room, and master bathroom and that kind of stuff to be tempered so they can walk on it barefoot, whereas the carpeted area they're fine with already. So sometimes we'll do that kind of thing where we temper the floor. You might hear that referred to sometimes as a staple-up system or an underfloor system. We call it staple up because traditionally you'd go underneath the basement floor, you'd lay all this tubing on the ceiling, and you'd literally staple it up to the ceiling. Now, obviously, you're not stapling through the pipe. You're stapling large staples around the pipe. More advanced ways exist now, right? There's clamps you can install on the ceiling, or now we have these like aluminum tray panels. One of our manufacturers, Rayhow, makes one called Rao panel. Those are very nice because that panel, you nail it up to the bottom of your floor from underneath, and you lay the tubing inside that metal panel. And that metal panel spreads out the heat more evenly. All right, so you can do that to kind of temper your floors if you want to do that. You can mix and match your radiant floors with other hydronic systems. Like I said, you can have a hydronic fan coil or air handler doing some tempering. You can have the new part of the house be on the radiant floor. The old part of the house may still have the old radiators. You could have your boiler servicing your radiant floor in your garage, but the rest of your house may have baseboard. You can mix and match all that kind of stuff. There's a little bit different tricks on how we pipe it, but you can mix and match that kind of stuff all the time. And like we said before, you can do snow melting systems, which we're going to talk about here in a little bit. You can heat domestic water with your boiler, all that kind of stuff. Oh, something didn't click there. Oh, there we go. Now it's clicking. All right, so where are we going to get the hot water from? There's lots of choices on where I can get hot water. By far, the most common choice for radiant floor systems in the modern era, meaning the past 10, 15 years, has been condensing boilers. Like we said earlier, condensing boilers like to operate at low temperatures because that's when they're the most efficient. Radiant floor systems need to use low temperatures so we don't burn people's feet, right? So they are married together very nicely in that 90 to 115 degree supply water temperature range. Perfect together. You can use non-condensing boilers, but like I said before, you got to have a mixing valve. I got to grab some cool return water and mix that in with your supply water to get the temperature low enough that I can put it through the floor and not piss people off. You can use an electric boiler instead of a gas boiler. Depending on where you're at in the world, electric may be all that's available to you. But if you have natural gas, in most cases, that is going to be significantly less expensive to run. You can use your geothermal system. A lot of you guys probably have heard of, water-to-air geo systems. There's also water-to-water geo heat pumps. So you still have the same kind of field loop out, buried in the soccer field, at the school or in your backyard at your house or whatever. And when the pipes come inside, instead of going to a water-to-air heat pump, they go to water-to-water. So we use that ground loop as the sink source for the compressor-based system to then provide hot or chilled water to your house. And the hot water, typically, we can't get 180-degree water out of a geo system. It's not really realistic without having a significantly oversized geofield. But we can get 110, 120, 130 degree water from our ground source heat pump system, and that is perfectly suitable for doing radiant floor systems. And of course, there's more extravagant things you can do, like if you're in a rural area, you can use wood-fired boilers. Obviously, you can use solar panels on your roof to do your radiant floor, although it's not the best application because most of your solar energy is in the summer and most of your radiant needs are in the winter, so they don't really match up very well. But we do typically use solar systems around here for doing like pool heating and stuff like that, because then the supply versus demand match up nicely. But you could do it for your radiant floor if you want to. And you could use a water heater. We are not fans of this at TEC. I know some guys do it. But you could use a regular water heater to feed your radiant floor. It seems kind of stupid to us that someone would spend all this money to doing all this radiant stuff and then cheap out and not buy the right boiler at the end and get an inefficient water heater to do it. Right? Why would I want a 60% efficient water heater when I can have a 94% efficient boiler? Plus, if I use a water heater, I still got to add other safety devices onto the water heater for using it on a closed loop system anyway. So it doesn't really make a lot of sense, but technically you could do it. Right? So I don't need very hot water to do this. Low supply water temperatures are suitable for radiant floor, so that means my water source can be much wider range of things than a normal building might allow. All right, we already talked about lower air temperatures in the building reduce the heat loss. Heat loss is a function of temperature differential. So the cooler it is inside, the slower the heat goes from inside to outside. So that's one of your energy saving things. You'll typically hear rules of thumb saying like every 3 to 5%, every degree you lower your thermostat, you save 3 to 5% on your energy bills, right? So you hear that kind of stuff thrown out there sometimes. We're using a more efficient source of heating to begin with the boiler. We're operating the boiler in its condensing range almost exclusively all the time, which does help us with energy savings there as well. And that's typically on the order of 10 to 20% more energy savings than that exact boiler would have had in a higher temp 180 degree application. It's almost always condensing. And it's also less expensive to move hydronic heat than it is to move air-based heat. Running a circulating pump is less energy consumption than running a fan, right? Air is a horrible heat transfer media. We use it for many reasons, and we almost kind of have to use it on the cooling side, for dehumidification. But on the heating side, we're not locked into air, and using water-based heating systems and running a pump is a better heat transfer mechanism because water, for a given volume, can move more energy than air, right? So that's kind of the reason there. So we pretty much take whatever you're spending now to run a blower, pretty much take it down to nearly zero to run a pump. I'm not going to say zero because that's obviously not true, but close. Big, huge reduction there. All right, so common residential applications. Basements are the ones that everybody wants, right, because the basement floor is always cold. You put a radiant system in there that takes care of that problem. Same with slab-on-grade type applications. In both of those applications, you do want to pay attention to what you put underneath the radiant tubing. Right? If I just put the radiant tubing down and then pour the concrete, well, for all the energy I have going up from the radiant floor up to my house and my building, I'm going to have some energy going down and heating the ground, which is not really helping me any. Right? That's just kind of an energy waste. So we do want to put some sort of insulation below the radiant tubing. Now, the ground itself is a fantastic insulator, so it's not like the outside of my building where I'm giving up heat to the outdoors and it's 0 degrees. Below my building, my ground temperature is probably in the 50s or 60s, so I'm not giving up a ton of heat, but I still don't want heat going down, right? So I'm going to put some kind of insulation under there. The two most common types are foam insulation, and some of the manufacturers make these foam panels you lay down that have these, what I'm going to call, I wish I had a picture, I should have put a picture on here. They got these little nubs, I'm going to call them, and you can use those nubs to kind of wrap and wind your radiant tubing around them. The other mechanism is to use some kind of foil-faced insulation, and we use some here, and we lovingly call it bubble wrap, right? Because it looks exactly like bubble wrap, that you have for packaging purposes, but it has a foil-faced insulation on one side of the bubble wrap, and you face that foil so it points upward, and then you put your flooring system on top of that, right? And that foil facing reflects the radiant heat back up. It'd kind of be like standing out in the sun and having a mirror and using that mirror to redirect the heat somewhere, right? Like when you were a kid, you probably directed it on leaves and started fires because you were a hooligan, right? Same kind of thing here. the foil facing reflects the heat back upward towards my building or towards my house. So if you're going to put it on the ground, meaning basement or slab on grade, you got to insulate underneath for it to go up. If you're putting this on floors in between, like I want to put it underneath, like in this picture here, on this giant master bathroom, which is not my house, by the way. If I'm going to put it underneath there and I have a conditioned basement underneath it, I don't care so much if some of the heat goes down. Now, I may want most of it going up because my basement probably has its own floor heating system, so I'm still probably going to want to put some kind of insulation under here to direct the heat upward, but it's not as big of a deal as it is when it's on the floor. Other common applications, garages, both residentially and commercially. Right now we're talking about residential, right? So if you're going to pour a foundation for a new house right now, I don't know why, if you were doing it right now, I don't know why you wouldn't put the tubing in your basement and put it in your garage floor right now, right? Even if you're not sure you want the radiant, at least put the tubing in, because once the concrete's poured, you're probably never going back and ripping that up. Put the tubing in. The tubing is the minor expense, and then later on you can decide if you want to do all the rest of the piping and the boiler and all that great stuff. But having it in your garage would be fantastic. Your garage door opens and closes. You don't lose all the heat immediately because the floor slab is such a huge mass. And then you can go out in the man cave whenever you want and avoid your wife. It's kind of the goal there. It's also fairly popular in apartment buildings. We do quite a few apartment buildings that have this type of heating. Dormitories as well, also fairly popular. Commercially, here's some of the common applications. This is a big one, car dealerships and garages. Those are the two biggest ones probably. Car dealerships, they don't like heating the air, right, because they're always opening the doors and the heat gets sucked out. So a lot of them have switched over to the infrared hanging heaters, which are fantastic because they shine down and heat objects, and they're heating up the ground as well. And then when you open the dock door, it doesn't go away. But the problem the infrared hanging radiant heaters have is they're heating everything they can shine on. Well, the one place they can't shine is underneath the car, right? And where's the technician at? Underneath the car. Now, some of you are saying, well, who gives a crap if the technician's happy? Well, apparently it's getting so cutthroat with these car dealerships to maintain good technicians that guys actually leave their company, their car dealership, and go to work for another company down the street because their buddy told them that it's warmer underneath the cars and it's more comfortable. We've literally heard of those examples happening. We do quite a few car dealerships with radiant floor heating. All the new ones that are built almost always have this. Plus, people drive in their cars with snow and stuff like that on them, and it kind of helps melt that snow off and drain that away. Garages, same thing, commercial garages. So if you got like a bus service terminal depot or something like that, a lot of those will go with radiant-based heating in them. We don't do a ton of warehouses, but we do a fair amount. Same kind of idea there. If the dock doors are always opening, I don't want my heat getting sucked out. Restaurants are not hugely popular, but we do see it sometimes. They want it on the outside on the patio area, to extend their beer garden hours of the year, if you will. Sometimes in office buildings and other places like that. So they're showing you some examples of car dealerships. Buildings that have longer-term outlooks, like universities, museums, governmental buildings, they tend to do this for the energy-saving type reasons, right? They're okay with having a 6, 8, 10-year payback on some installation because they know they're not going to be giving up buildings that quickly, right? A university buys a building, they keep it for 200 years. So they're not worried about an 8-year payback, typically. So longer-term outlook buildings tend to want to do radiant-based heating and cooling as well. Retirement homes are very popular for radiant. You got a couple classes of retirement homes. You got the ones that people kind of unfortunately have neglected, and then you got all these new fancy ones that people are building that people want to put their family members in, right? And old people are always cold, right? They don't have great circulatory systems. They're always cold. The radiant floor helps keep people much warmer, much more comfortable in their elder years there. Same kind of thing with daycare facilities, but opposite, right? Little kids and little babies, they want to be warmer. We want to keep those people warmer as well, right? The daycare, those kids are crawling around on the ground playing the whole time. It's a little bit different than a high school kid who's standing up and sitting down. These little kids are on the ground. Why don't we heat where they're at? Heat the floor, right? So that kind of thing. Prisons are a great application, right? Because in a prison, we want everything to be tamper-proof. Well, it's a lot less tamper-proof when it's buried under a couple inches of concrete. So anything we can bury, any tubing we can bury in the ground or in the wall cells and things like that versus having ducts where people can take the duct grates off, big difference there. I realize there's tamper-proof grates and all that, but nonetheless, if it's buried in concrete, they probably don't even know it's there, let alone know how to get the concrete off of it to get to the tubing. But I'm sure they'll figure it out. They got plenty of time on their hands. Hospitals are another great one. So those are some of those kind of examples. It's not uncommon to see floors like this before we pour the concrete, and you need somewhere to have all these headers come in. So here's one example showing you a box in the floor. Here's another one showing you on the wall. The wall is by far the more preferred method. You can also see that when we put them on the wall, we typically put these two benders in. So when they come up the floor, we kind of have a nice clean bend upward, and it makes it a little bit easier. A couple of guys have asked about these two benders and wanted to put them on every single tubing turn in the floor. That's not what they're for. They're for the floor-to-wall transition point. But we'll lay out all these circuits on the floor. We'll help you design the circuits and kind of plan them out. Like we said before, bus repair terminals are a common application. Fire stations, almost every fire station we've done in the past 10 years have had this. Right? The fire truck leaves. They leave the door open for whatever reason. All the heat gets sucked out. They come back 25 minutes later after the false alarm and pull in. Well, the radiant floor keeps that heat way longer than the air would. Airplane hangars, also fairly popular, that kind of stuff. Anytime you got doors opening and closing a lot, it becomes more of a no-brainer to do radiant-based floor. So these are just some of the institutional type applications that we just mentioned. Agriculture is also a popular one. Bill Bailey in our office, who does all of our radiant layout designs for contractors and engineers. If you don't know Bill, you should definitely buddy up with him. But he does a lot of dairy barns. Got to keep the cows warm. There's tons of studies out there that the warmer the cows are, the more milk they produce. So you can actually put radiant in a dairy application as a payback technology, if you can believe it or not. And I'm sure there's similar logic with some of the other animal facilities. And then greenhouses for planting. If you want plants to grow year-round in a glass cold box, you better find a way to heat them. And if you put in ceiling-based, unit heaters and things like that, they are going to eventually get wet from all the moisture you're putting into that building and not do as well. Radiant floor doesn't have that problem, obviously. Sporting arenas are a good application as well. I believe both Soldier Field and Toyota Park locally have radiant heating underneath the fields to keep the grass roots growing. It doesn't seem to work at Soldier Field very well. The field sucks there, but I shouldn't say that. The field's fantastic. But it does seem to work very well at Toyota Park with the Chicago Fire play. But if you want grass to grow in the winter, you're going to have to put something under there to keep it warm. So we do that as well. So that kind of stuff. All right, so that's kind of a primer on radiant heating, and then we'll talk about Snowmelt here in a second. I do want to mention a few things on radiant cooling because it always seems to come up when we talk about radiant heating. You can definitely cool a building with radiant technology. This is done all of the time, but it is nowhere near as popular as radiant heating. The main reason is with radiant cooling, I don't have any way to dehumidify the space, so I need to have something else doing the latent control. If I just have radiant cooling, chilled water running through these pipes, it's going to cause a condensation issue on the surfaces, which is the floor, and people are going to get injured. So I have to have some way to dehumidify the air. So typically radiant cooling, whether it's in concrete slab stuff, or whether it's panels, or whether it's chilled beams or something like that, is going to have to be coupled with a dedicated outside air system to handle the latent loads of the space and the ventilation needs of the space. But you certainly can do radiant cooling, and we have done projects that way. Generally, it's only commercial. Residential is a little bit harder because you have too many things occupants can do, although we have been to a house that has radiant cooling just because the guy wanted it, and it is pretty cool. But when he sells it to someone else, I fear what will happen. But in commercial buildings, it's a little more controllable through the building automation and stuff like that. So just keep that in mind. You can do radiant cooling, and that's a whole other topic. If you want to learn more about that, I believe we have a recorded webinar on that, and if you need more information, I can certainly assist you with that kind of stuff. All right, so we're going to stick on the heating side for today's purposes, and we're going to kind of skip along a little faster here to get over to the snow melt stuff here. So radiant snow melting and ice melting systems look very similar to radiant heating systems. The main two differences are A, it's outside instead of inside, right? And B, I'm not doing it necessarily to keep people warm. I'm doing it to keep snow from accumulating on my surfaces, meaning sidewalks, driveways, things like that. Right, so there's several different drivers for why people would want this. Residentially, people want it because they want it, right? When it snows, they want their driveway to have no snow, and they want to see their neighbor shoveling when they're not, right? It's kind of a status kind of thing. Commercial, we have much different reasons that we'll talk about in a little bit here. But it is a little bit safer as well, right? People you hear all the time slipping while they're shoveling or snow blowing and getting hurt. Snow melt kind of reduces those risks. Since you're not using any salt to protect from the ice, it does help with the longevity of your surface. If you got, asphalt, maybe you don't care. You just keep repouring it every 5 years. But if you got, the nice bricks like these people have here, you probably don't want salt getting in the cracks and ripping that stuff apart over time. All right, so that's kind of some of the reasons with that. Commercially, we do it in a lot of different spaces. We do it at the exiting, leaving area of car washes, right? Because we don't want the water dripping off the cars, landing on that surface, turning into ice, and then when the next car leaves, he slides across our parking lot and we get sued, right? So we kind of not only use radiant to heat inside the car wash, we also heat the exiting area to keep it melted, that snow from or the ice from forming on there. It works great on walkways, ramps, driveways. Once again, athletic playing fields, anywhere you want to be able to get rid of snow and you don't want to have to plow it and shovel it because that might damage the surface, it's going to be ideal. So there's things that we got to think about. We got to think about where we're at in the world, what our typical air temperatures are, how much snow am I expecting to see a year in this area, how fast might the snow come down, and with some of those kind of factors. What you don't want to do is promise someone that, hey, I'm going to put this snow melt system in and you'll never have to shovel snow again no matter what. Because as soon as you say no matter what ever again, there's going to be some giant blizzard the next year. Since I've been working here at TEC, we've been doing snow melt for about 10 years. And I can only think of 1 year, which is about, I think, 2 or 3 years ago. We had that blizzard-like conditions that we heard about some of our customers and snow melt not keeping up. You can't plan for everything, right? It's just not realistic. So don't overpromise that kind of thing, Use things like 99% of the time kind of thing. You also got to think about when snow's falling, right? It doesn't snow very frequently when it's -5 outside, right? Generally, it's too cold for it to actually snow, right? So most of your snow events occur between like 15 and 40 degrees outside, or we're saying here 10 to 35 degrees outside, or when most of your snowfall is going to occur. Some of you guys in your cars have the little snowflake warning that pops up telling you it might snow. It's not because your car is super smart and knows that it's going to snow. Right, it's no better than the weatherman. It just knows it's between this range, so it pops up a little snowflake to warn you the temperature conditions are right for it to snow. The good news about that is that my boiler system for heating my building is probably designed for a 0 or -5 or -10 degree day. So the time that it's going to be snowing and I'm going to be melting snow is not typically my design heating day. That means in most cases I don't have to upsize my boiler. I can use my existing boiler and just grab some of his available heat to go melt my snow. Now, some applications, the snow melting becomes a more dominant load than the space heating even, and we got to do it a little bit differently. But if you're just talking about your house and you want to go heat some snow on your sidewalk, that would be pretty easy. If you got, a 2,000-foot driveway, a little bit different discussion. We're going to have to size your boiler differently. All right, so we got to think about what we got to melt and how much of it we're going to do. We generally have 3 classes of snow melting systems. I will mention all 3 classes here in a minute. So you got to figure out what class your project's going to fall into, and then you got to go look at some weather data to see, well, what's my snow expectations and what are my temperature expectations for the region that I'm in. And we'll show you some examples here in a minute. Mike actually typed in a question asking, what's the average lifespan of a non-condensing boiler? If you look at the ASHRAE Handbook of Fundamentals, they give you lifespans for typical equipment. And I believe for non-condensing boilers, they give you 2 numbers in there, depending on what metal it's made out of, but the range is 25 to 35. I believe the cast iron ones are more towards that 30-35 range, and your steel boilers are more in that 25 to 30 range. So for non-condensing boilers, that's your answer there, Mike. So on the snow melt, figure out our loads, size the heat source, space our tubing, and then we got to do our normal hydronic stuff, right? Determine what our flow rate is to get the BTUs that we want. Determine what our pressure drop is through our piping loops. Size the circulator accordingly, and then figure out the controls. Controls are the interesting parts. We'll talk a little bit more about that. The rest of that stuff is normal hydronic sizing. The 3 classes of systems are 1, 2, and 3. Typically 1 means residential. Typically 2 means commercial, and typically 3 means institutional. There's nothing that prevents you from putting a commercial system in a residential driveway and those kind of things. So that's just kind of just a terminology that we use to kind of gauge what kind of systems we have. The class 1 basically means we're trying to be able to melt the snow 98% of the time. So we're sizing for those kind of weather events. versus other classes of systems who may be sizing it for 100% of the time because it may be more critical, right? So it's just a kind of, involves how we decide to size the boiler and space the tubing and so forth. But this is perfectly fine for most residential applications, driveways, sidewalks, porches, that kind of stuff. You may get a little accumulation, but the system will eventually catch up and melt it all. They're just showing you what a typical driveway might look like while the snow is actually falling. You can see it falling in the background there, but on the driveway it's melting off right away. By the way, you also got to think about drainage, right? These driveways need to be sloped away from things you care about, like your garage. So this one's sloped towards the street, so that's good. And probably the reason they did it is because they got this brick layout, and if they were shoveling, snow blowing, or plowing that, it would probably rip it up pretty good, and the salt would get in the cracks and rip it up pretty good. I love this one because this dude paid to put the snow melt in and took this wonderfully beautiful picture, and he can get out of his garage no problem, but then he gets to the street and his neighborhood doesn't even plow it. So it's just an interesting one there. Class 2 systems are commercially oriented, and our goal there is to be able to handle 100% of the load. It doesn't mean we're going to melt it all immediately, right? But it means we're going to be sized so that we could melt it all. So we may accumulate a little snow at the beginning, but we'll eventually catch up when we turn the system on. So this is good for sidewalks, steps, things like that. People expect to wait a few hours for someone to shovel it. You'll just be snow melting it instead of shoveling it. There's just some pictures of that kind of stuff, sidewalks. Parking garage ramps are actually a huge application. We do quite a few of these because it is difficult to drive your car up an icy ramp and get out of your parking garage without sliding backwards into someone else's car. So we do quite a these kinds of applications, and it doesn't really take that much energy because you're not doing like a whole parking garage. You're just doing this one ramp. So we do that quite frequently. And you can see over there on the right-hand side there is a sensor on the wall to turn the system on, and we'll talk about controls here in a minute. So parking garage ramps are a big application. You can put this in concrete, you can put it under brick, you can put it under asphalt. All of these types of materials will work well. Sidewalks are popular, steps are popular. It's a big slipping hazard. By the way, a lot of buildings that decide to put this in their sidewalk, like in front of their downtown building or in the steps of this church or whatever, they're mainly doing that for lawsuit avoidance reasons or just because they like their customers, right? They don't want people getting hurt slipping in front of their building. Right, so if there's no snow there and no ice there and no accumulation there, and that ground is dry compared to the other neighbor's ground, they're probably not going to be the ones that get in trouble. Class 3 systems are typically our institutional type systems. So this comes up a lot at hospitals, ER drop-off bays for the ambulances, the helipads, right? These kind of applications where I cannot tolerate any snow on there whatsoever. I'm willing to pay more to operate it to make sure there's no snow on there at all at any point in time, right? Because the surface being dry versus wet is more important to me than the energy cost in those kind of examples. So generally we have 3 ways that we control snow melt systems. I'm going to start from the bottom up. That number 3 method is the manual one. That means I look out my window and say, oh crap, it's snowing. I don't really want to shovel. I'm going to go flick this switch on, which is going to turn on my snow melt system, which is going to enable my pump in my boiler and start sending warm water out to my system, right? The problem with that system, as you might gather, is I say, oh crap, I turn the switch on. When do I say, oh crap, and turn the switch off? When I get my utility bill, like 4 weeks later. Oh crap, I must have left it on all month long, nonstop, running balls out, right? So that we never use this kind of control at our office. If you want that in your control system, we won't even sell it to you, right? Of course, it's just a light switch. Anybody can get it. If you want to do it manually, we prefer the number 2 method on this screen here, which means we've got a little bit of control. And instead of a regular switch you turn on and then turn off, we use a timer switch, right, like an 8-hour timer or whatever, right? So you spin the dial, turn your snow melt on. 8 hours later, if you forget to turn it off, it turns off for you. It's nothing more than a wind-up timer like you'd have for a bathroom exhaust fan or something like that. It's very, very easy to install, and it's very low-cost type control. The more preferred method would be number 1, which would be an automatic system where we look at the temperature of the slab and the moisture in the air to determine if it's even time to put it on, if it's likely to be snowing. Right down in the bottom there, you can see there's a picture of a little enclosure box. On top of that box is the moisture sensor that we use very frequently. This one's from ETI. So you put this outside, right, obviously, and there's a little electric grid. I don't know if you can see it through the webinar or not, but there's a little electric grid on top of this guy. And if there's moisture on there, meaning snow or water that lands on there, that moisture completes the electrical circuit between those various lines on there. And if we complete that electrical circuit, that closes a relay that says, boom, it's moist outside, right? I have water or snow on me. So he says it's moist outside, so it means I got water or snow. And then I got a temperature sensor, an outside air temperature sensor that says if it's below 38 and I see this moisture sensor, it must be snowing. If I see the moisture sensor and it's above 38, it's probably raining, not snowing, so I don't care, right? So it's got to be cold and wet, and then we turn it on. That's a common one that we use. You can also use the slab sensor ones. I'll show you a picture of one of those in a minute. We lovingly call them the hockey pucks. You bury them in the concrete. But the one we're showing you here, you can just put, on the side of the concrete, behind a bush, something like that. All right, so let's look at a couple quick examples here. Jason actually typed in the cost difference for the controls. Obviously, number 3 is just a switch, so that's 0. Number 2 is a timer switch, so that's like, $10. And number 7 is automated sensors. So let's say, for sake of argument, it's like $500 worth of sensors and wiring. We can look it up if you need the exact cost, Jason, but it's kind of on that scale. The more interesting thing is how much difference in operating costs might it be, right? So there's the initial first cost of buying these controls versus operating costs. So we'll look at a couple examples in that regard. So here's a residential example, and we'll look at a couple other ones too in a minute. This one's 1,000 square feet of surface area that I want to melt, which is obviously not that picture of that particular driveway. So I've got 1,000 square feet. I need about 125 BTUs per hour per square foot in order to take care of this load. So I'm estimating that it's about 150,000 BTU output demand. If I got 6 inches of concrete, that equates to about 75,000 pounds, right? And you're not doing this when you're designing a system. We're doing this right now to kind of look at a cost example. And then on average, we're going to say, for this argument, at 18 degrees is when our snowfall normally starts on average. Some days it might be 10 degrees, some days it may be 25, but let's just say 18 for argument's sake, because we've got to calculate something. And let's say there's 10 times a year that I get snow that's a significant quantity that's worth melting. And let's say it takes 8 hours for the whole snow to fall to happen and for me to finish melting it all off. So it's 80 hours of actual melting time per year. I got 2 different kinds of loads that I have to deal with here. I got the pickup load, right? How much is it going to cost me to get the slab up to temperature where it could actually melt something? Then I have the actual load of melting the snow itself, right? So how much did it take me to get the slab up to temperature, and then how much more energy did I spend to melt it? So based on that example we just given, that comes out to about 3.5 million BTUs per year for the pickup load, and about 12 million BTUs per year of the actual melting load for that 1,000 square foot system. Depending on your gas costs, so in our case we were assuming $1 a therm, right? So those two costs, 3.5 million and 12 million, added together is 15.5 million total BTUs per year of output that I need. If I use a 93% efficient condensing boiler, that basically comes out to $165 a year for me to operate this system in that particular manner. Right? It's me manually turning the system on and letting it come up to temperature and then melt the snow. That's plan A, right? So plan B is let me do some automatic controls, but I'm going to idle the slab so that way I don't have to wait as long for my pickup time. So I'm going to keep the slab a little bit warm so it doesn't take as long to get there. There's a picture of that hockey puck sensor I was talking about. Typically you bury that in the concrete, right? We use the other kind when you forget to bury this one in the concrete. But it works in a similar fashion. I'm detecting that slab temperature and deciding if I'm going to have a snow melt event or not. So keeping the same 10 snowfalls per year. The difference here in this case is I'm going to keep the slab maintained at 28 degrees Fahrenheit, right? But I still got to get up to 38 or higher to melt the actual snow. I guess technically you can melt it at 32.1, but that's take forever, right? So we say logically 38 or higher to start melting the snow. But I keep the slab at 28 degrees. So that's going to cost me some money throughout the winter to keep it at 28 degrees. Any day outside it's less than 28 degrees, I got to pay to heat it up to 28. But it means when it snows, I can recover faster. So we're going to assume 2,000 hours in the wintertime of potential that I have to deal with here. And it's only below freezing 70% of the time, so 1,500 hours we're going to assume. So 1,500 hours of the winter, I got to heat this slab up to 28 degrees. All right, so let's look at the math and how that's a little bit different. So now instead of just the pickup and the melting, I also got the idle load. So the pickup load, it gets me up to temperature, right? But it's going to be less than it normally was because I'm starting at 28 degrees already. So in this example, it's basically half of what it used to be. But you see the idle load is a lot. It's 75 million BTUs per year. So I got 2 million BTUs per year to pick it up on those 10 event days, 75 million BTUs a year to keep it idling at 28 degrees all winter long for me, and then 12 million to actually melt the snow. So in this example, for that 1,000 square foot slab, it's going to cost me like $950, right? Versus 165 for my basic control, which is the on-off switch or the timer. This is why residentially you'll see most people with small systems just opt for the little timer switch, right? Because it's going to cost them less to operate it throughout the year. $160, that's nothing. I mean, you could pay someone to shovel for that amount of money and do a worse job. $950 is quite a bit of money. So high-end custom homes, those guys may choose to use the automatic system. Everyday folks are more likely to use the timer switch idea. Then there's Plan C, which is the always-on critical application load. So this is what we're using at hospitals, helipads, stuff like that, where we want no snow accumulating for no minutes of time. We want to melt it as soon as it touches the slab. We want to start melting immediately, right? So in that case, there is no pickup load because we're always keeping it at temperature. There is no idle load because we're always keeping it at temperature. It's just the total amount of energy I need to heat it all the time, year-round, no matter what. So that comes out to about $1,200. So $1,200 for the critical applications. You put a little bit advanced controls on there. For non-critical applications, $950. And then if you want to use a timer switch, $165. And by the way, these are all based on $1 a therm. And as you know, gas in Illinois anyway has come down quite a bit. It's more like 65, 70 cents. So you can chop a third off of any of these numbers if you want, a today cost. And then 5 years from now, it'll go back up and it'll all be different, but nonetheless. So main reasons are safety, lawsuit avoidance, that kind of stuff for these commercial snowmelt systems. And I'm going to skip some of these things here. And we'll skip the radiant cooling discussion. There are buildings in this area that do have radiant cooling. So if you want more information on those, let me know, and we'll get you talking to the right people for that. There's lots of different ways to do the radiant cooling type stuff. Last thing I'm going to leave you with, we do a lot of stuff with Rayhow, as most of you guys probably know. Most of our heating systems and snowmelt systems, Bill in our office designs them for you guys in-house. When it comes to radiant cooling, we tend to lean on the Rayhow guys to help us design those, a little bit more involved. And they also do control systems specifically for radiant. So radiant heating, cooling, snow melting, ventilation needs, geothermal. Their system can control all of these things together in unison. So if you need help with that, let us know, and they can help us lay out a radiant control system for your house or your commercial building or whatever you're working on. That's a little more specific to what we're trying to do than just cobbling together a bunch of thermostats and relays, which is the old way of doing it. All right, so does anybody else have any further questions that I need to try to address? Let's see. We got Matt, we got Mike, we got Jason. I think we got everybody's questions that is on here. If you got any other questions, go ahead and type them in. If not, my email is on the screen, as well as my cell phone number. You can hit me up later if you want to ask something. If I don't know the answer, I will find it. If I can't find it, I will find someone who can find it, and we'll get you taken care of. So with that, looks like there's no more questions, so I'm going to go ahead and stop the recording and end the webinar. And within a couple hours, this will be posted online, so if you got coworkers who want to watch it, they can certainly do so. I thank you guys for your time, and we will talk to you next week.